So this is the presentation I gave for my defense, um, and it's on controllers and control insights for the BIRE aircraft. And then we'll get into what the BIRE aircraft is. So just a brief roadmap of where we're going. I'm going to give a little bit of background to flight control and dynamics, and then talk a little bit about some of the models we use to simulate and control the BIRE aircraft. And then I'll move on to an interesting property of the BIRE aircraft that it has multiple trim solutions at a given flight condition. And then I'll talk a bit about some different controllers that I look at in my dissertation, linear stabilization controllers, gain scheduling, some of those linear stabilization controllers, and then a last step looking at tracking controllers, both linear and nonlinear. And then we'll wrap up. Okay, so I want to give a little bit of historical context. So in 1903, the Wright brothers performed the first powered, controlled, sustained flight. Um, and what I'll mention here is that it was the first controlled flight. And one interesting thing, they were very inspired by watching, they were very interested in watching bird flight. And so they actually developed their wing warping mechanism. So they would twist one wing one way and the other the other. They developed that by watching birds fly and seeing how they controlled flight. And the second interesting thing about this flight that I'll point out is that when they controlled this wing warping, they tied the control of that to these rudder uh, surfaces on the back. And they did that. That coupling was done to help them coordinate turns. Okay, fast forward 11 years was the first automatically controlled flight. So the Sperry's, Elmer Sperry and his son Lawrence, developed an automatic stabilization system for an aircraft. And they went out and this is the son Lawrence in the cockpit. This is a mechanic, and they had the mechanic stand up and walk along the wing. And the son Lawrence took his hands were completely off the controls, and the aircraft stayed steady level. And what I want to point out here is that this wasn't the first automatic control system for an airplane, but it was kind of the most successful, most widely known ones at the time. And that stemmed from their selection of which states to feed back in the control system. Okay, so we had our first controlled flight, our first automatically controlled flight. And this here at the bottom was the first computer in the loop controlled flight. So this was a C-54 run by the Air Force. They outfitted it with a throttle controller and a stabilization controller, and a computer run by punch cards. Uh, they uploaded the program through punch cards, and the computer controlled the entire flight. From they flew from Newfoundland to the UK, and from starting ground roll all the way to landing and decelerating, no human hand touched the controls. Okay, so this is a little bit of background on flight controls. Um, but so this computer in the loop control system we've talked about here, if you've ever been on a commercial airliner, you've been on an airplane that has a computer in the loop control system. Usually they have something like a yaw damper or something like that to help the pilot a little bit or provide a little bit more comfort for passengers. Um, but fighter aircraft, there is a family of aircraft. The fighter aircraft do not. They need to have a computer in the loop control system, and there's a reason for that. They are so unstable. They are unstable to the point that a human pilot could not fly the aircraft. And why would they even do that? Well, it comes down to these 3 points that I've got here on an aircraft like the F-16. The first is the center of gravity. So that's the point where we sum all the mass. We can pretend that it's a point mass at that location. The second is the neutral point. This has a little bit more to do with the aerodynamics and flight dynamics. This is the point where the change in the pitching moment with respect to angle of attack is zero. In other words, what that means is if the center of gravity is forward of that point, the aircraft is stable in pitch. If the center of gravity is aft of that point, the aircraft is unstable in pitch. Now, why would they fly unstable with the center of gravity behind that point? Well, it has to do with this third point here, this maneuver point. And this is the point where the control gradient is zero. The high level just understanding I'm trying to get across is the closer the center of gravity is to that maneuver point, the closer this guy is to this guy, the more maneuverable your aircraft will be. And so to take advantage of that with fighter aircraft, they slide that center of gravity as close to that maneuver point as possible. And as a symptom of that, it generally lies behind this neutral point so that the aircraft is unstable and they need to have some sort of computer in the loop control system. Okay, so now that we've talked a little bit about that, I'll present the BIRE aircraft. Excuse me. So this is the bio-inspired rotating empennage. That's what BIRE stands for. It has four control inputs: the ailerons, which deflect asymmetrically, the stabilators, which deflect symmetrically, the rotating empennage that rotates about this fuselage axis. And so you can imagine the aerodynamic effect of deflecting the stabilators is going to depend on whether your tail is rotated or how far rotated. And the last control effector that we have is our throttle setting to give us propulsive power through the engine. Okay, so the BIRE aircraft, bio-inspired, again, that's bio-inspired rotating empennage. The BIRE aircraft is a bio-inspired asymmetric fighter aircraft. And it's kind of the amalgam of all these three areas of research. Now, there has been tons of research performed looking at bio-inspired controls, aircraft controls, asymmetric aircraft controls, fighter aircraft controls. This work is kind of the blend of those three bodies of work. Now, there's a couple interesting things that we can learn from those various areas of work. The first, particularly with asymmetric and fighter aircraft, there's quite a bit of coupling in the system, in um, so much so that whereas for a traditional aircraft we may have a pitch controller, a roll controller, a yaw controller, we can't really do that. We have to do some sort of blending, perhaps pitch and a lateral controller or something like that. Um, and for asymmetric aircraft, it's even a blend of all three. Now, we already mentioned that fighter aircraft are generally unstable. So that was something that's definitely looked into in fighter aircraft controls. Um, as far as bio-inspired aircraft are concerned, a lot of groups, especially the groups that look at rotating tail aircraft, have found good success or suggest that there would be good success with using nonlinear model-based control. And we'll talk to that a little bit at the end. And then the last is one group that did look at a fighter aircraft with a rotating tail, found that it had multiple trim solutions, and we'll come to that in a moment. Now, before I get to the models, I'm just going to describe the objectives of this research. So the first is to design and evaluate a nominal linear stabilizing controller. The second is to design and evaluate a gain scheduled version of that linear stabilizing controller, and we'll get to what that means in a moment. And then 3 and 4 are kind of tied together. It's to look at tracking controllers, both linear and nonlinear, and compare their performance, um, and determine which one would work best for the BIRE aircraft, if any, if we could get any to work right. Okay, so now let's talk a little bit about a high-level overview of the dynamics of this system. So we have this aircraft state that's pictured up here. This x, so it's a function of our aircraft body fixed velocities, body fixed rotation rates, earth fixed position, and earth fixed orientation. And then down below we have our commanded control U and our actuator state delta, and those have an aileron component, stabilators component, tail rotation component, and throttle setting. Okay, so our control and our actuator state and our aircraft state, these two feed into our aerodynamic forces and moments. Now, this was work done by Christian Bolander. He developed a lot of fits and a model that we could use for control design of the aerodynamic forces and moments for the BIRE aircraft. Now we get those forces and moments that, with the aircraft state, feed into our aircraft equations of motion. Now, one interesting property of the BIRE aircraft, as you can imagine, if we rotate this massive tail, it's going to change the mass properties of our vehicle enough that we need to account for it in the inertias. And so we have our inertias, that's why it's outlined in purple. We have our inertias that are a function of our tail rotation that feed in with all these other things to give us our aircraft equations of motion. And once again, that's our dynamics. That's what we can use to simulate for control design, etc. Okay, and down below, we have this same aircraft state and actuator state, and those feed into our controller to give us our commanded control, U, and that with our actuator state delta can be used to determine our actuator dynamics, and that can help us simulate these actuator dynamics. Now I'm going to dig into a little bit these aerodynamic forces and moments, this modeling that was performed in previous work. Whereas for a traditional aircraft, one way that we could model the yawing moment is shown right here. We'd have some sort of set of stability, damping, and control derivatives, and we would implement the effects of each of these aircraft states and actuator states multiplied by those to give us our total yawing moment coefficient. That's one way we could model the aerodynamics. Um, if we were to do something similar for the BIRE model, as we have done, this is the yawing moment coefficient equation, and you can see that we have, not only do we have these extra terms, so like for example this C and alpha term that didn't show up in the traditional model, each of these C derivatives that up here were constant for the traditional model, those have a hat on them down here for the BIRE model, and that indicates that that coefficient is not constant, but is a function of the tail rotation. It follows this sinusoidal fit. And so this goes back to that work done by Christian Bolander. He ran a whole bunch of aerodynamic data and produced fits for all of these coefficients to this aerodynamic data. Um, and so that, I'll talk about the challenges right now, but that's one particular challenge is that we're nonlinear in tail rotation. Okay, so that's the first challenge. We're nonlinear in tail rotation. You can see that all of these coefficients follow this form, each have an amplitude, a frequency, a phase shift, and an offset. Now, some are stronger functions of tail rotation than others. Um, but so once again, it's nonlinear, but also we're not control-affine. So you can see this delta B is buried inside of a sine function, and each of these are multiplied, so we get cross-coupled terms and things like that. And so it can be some control methodologies may be difficult, if not impossible, because of that fact. Okay, a second control challenge, like I mentioned earlier, is that we have all of these. The yawing moment is typically traditionally a lateral moment, but it's dependent on all of these longitudinal states as well. So we have angle of attack, we have pitch rate, we have stabilator deflection. Okay, and that definitely further enhances the argument that we'll need to develop some sort of multi-input, multi-output control this system. Okay, now another challenge that we have is that some of these terms, particularly the terms that are multiplied by a control effector, go to zero at certain tail rotations. So for example, up in this plot over here, we have Cn delta E, that's this guy down here. At a tail rotation of 0, negative 180, positive 180, our control derivative is 0. And so in those scenarios, we cannot use the stabilator deflection to produce a yawing moment. And so that may cause difficulty in certain control scenarios. Okay, so I mentioned that I'm putting actuator dynamics in here. Now, not only do we have limits on how far those actuators can actuate, but we also have rate limits on how quickly they can move, the rate of how quickly they can move. So the tail rotation rate limit is 50 degrees per second, so it can be up to that 50 degrees per second, but no more. Now that's a little bit lower than more traditional rate limits on more traditional aircraft surfaces. The ailerons are 80 degrees per second. The stabilators are 60 degrees per second. Part of the reason for that 50 degrees per second being so low, why it's so low, is because our tail rotation, we're rotating this massive heavy tail. And so one way for us to kind of uh, not necessarily model, but account for how hard it would be to rotate that tail is to put a low limit on there, and that's an estimate from our the from the actuator studies that have been done. Okay, so we mentioned that the baseline a fighter aircraft is statically unstable in pitch, and the BIRE aircraft is certainly statically unstable in pitch, but it's also, because we've removed that vertical tail, it is also statically unstable in yaw. Okay, and then the last challenge that we'll have to deal with is uh, when we trim the aircraft, the trim stabilator input is practically zero at a very specific flight condition, but it's the combat maneuvering flight condition for the aircraft, and so it's certainly one that we anticipate to be at a lot, right? Um, and this is great for aerodynamics to have basically zero stabilator trim. That means we're going to have lower lift produced by the tail, so lower drag. Um, and so that's wonderful from an aerodynamic standpoint, but for control, if you can imagine, the trim stabilator input at the flight condition that we'll mostly be talking about today, 15,000 feet altitude, Mach 0.6, at that flight condition, or the trim solution for steady level flight at that flight condition, the trim stabilator input is basically like zero 0.1 degrees or 0.01 degrees. It's tiny. And you can imagine if we rotate the tail with 0.1 degree stabilator trim, we're going to have a lot smaller yaw force that we produce with that tail than if we were to, say, have a trim stabilator input of 5 degrees or even 1 degree. Um, the yaw force would be quite larger, quite a bit larger if we had a larger stabilator trim input. Okay, so we've talked a little bit about these control challenges. I'm going to address very briefly the multiple trim solutions, and I go into this in quite a bit of detail in my dissertation. So when we try to determine what a trim solution is, we are trying to determine what the aircraft state and the control should be to set our dynamics equal to zero. For a traditional aircraft in, say, a steady coordinated turn, there's usually only one solution to that problem. There's only one, basically, U that we could use to stay in that steady coordinated turn for forever. Such is not the case for the BIRE aircraft. There are generally three trim solutions, one with the tail negative, where the left stabilator is down. So these are looking at like in a right turn. One with the tail near zero, and one with the tail positive, so right stabilator down. And that's plotted over here on the right. So this is as a function of bank angle in a steady coordinated turn, the tail rotation on the y-axis. We have these various points. The diamonds indicate the baseline vehicle, so with a vertical tail, no rotating tail. The circles indicate the tail near zero solution, and the plus signs and the minus signs indicate these tail positive and tail negative solutions. Now, once again, I go into this in the dissertation, just a couple interesting things that I found there. The alternate solutions, this tail negative or tail positive solution, those are generally lower in drag, lower in throttle setting, and generally require lower control effort to regulate a disturbance in a given rotation rate. But they also require larger control deflections. You can see that pretty obviously right here. And the linearized systems, if you look at that, the eigenvalues indicate that the alternate solutions have a higher rate of divergence. Okay, so now I'm going to move on and talk about some of these controllers. I'm going to go pretty briefly over linear stabilization and gain scheduling. I'm going to spend a little bit more time on these tracking controllers. But if we linearize the aircraft dynamics, it's a nonlinear system, but we can linearize about some trim solution, and we get this system here. So we have an A and a B, and we have our linearized state, our linearized control. And this is our full control here to stabilize about this trim state. So we can use this A and a B with a set of weightings. We can use LQR to get a set of gains to stabilize the system about this trim solution. And you can look in the dissertation for more information on how this is developed. But these gains, I'm just going to point out some interesting things. First, the aileron command is primarily dependent on yaw rate. The stabilator command is primarily dependent on elevation angle. The tail rotation command is primarily dependent on yaw rate. And the throttle setting is primarily dependent on elevation angle. Now, I'm going to give just a brief representative response of the vehicle So I'm going to explain this real quick. So we've got x-axis, we have time on the x-axis in these plots, and then on the y-axis we have our body fixed velocities in the linearized system, our body fixed rotation rates linearized again, and then we have our full control over here in the linearized system. Now, um, let's see. What we're doing here is the aircraft starts off at trim, and then it has some non-zero initial condition in roll rate, pitch rate, and yaw rate, and we're damping that out and bringing the aircraft back to the trim state. In the dissertation, I go into quite a bit more detail about this. I looked at regions of attraction in non-zero initial conditions and rotation rates. I also looked at regions of attraction with multiplicative aerodynamic model error. Um, Something interesting I found there was that uh, looking at the percent success within this region of attraction, if I were to hold the tail rotation fixed, in other words, keep that at zero this whole time, uh, in the case of steady level flight or some value for the steady coordinated turn, and only use aileron, stabilators, and throttle setting to stabilize the aircraft, that percent success doesn't really change. That region of attraction doesn't really change if we hold tail rotation fixed, and that was an interesting result of that study. Okay, so I'm going to move on to gain scheduling. So here the idea is we were talking about linear stabilization controller, which works in a certain region around this trim solution. Outside of that, doesn't work so well. How large that region is, well, that's what we can estimate the region of attraction through Monte Carlo analyses. Um, but the idea of gain scheduling is what if we had one trim solution and we had a second trim solution inside of the region of attraction of the first trim solution, and we have a third one inside the region of attraction of the second trim solution, and so on and so forth. So you can kind of imagine just this line of bubbles that intersect. Um, the idea of gain scheduling is if we can have our bubbles large enough or create enough bubbles, we'd be able to cover basically the whole region of wherever we're flying, the whole domain, in this case, the flight envelope. And so you can see that we have this linearized system as a function of Mach number, altitude, and bank angle. Now, Mach number and altitude, those are pretty common scheduling parameters in aircraft controls. However, bank angle, not so much, but I'll get to why I have that in a second. It has to do with rolling into a steady coordinated turn in some of the studies I did there. Then we have this full control here. I don't have the gains because, again, there's all these gain scheduling points, and so I'd have to have several matrices of those large matrices. A lot of the predominant components, like I show in for the linear stabilization controller, are similar, but you can look at the dissertation for that information. So this, in the dissertation, I do look at a change from one Mach number in altitude to a different Mach number in altitude. For sake of time, I'm just going to look at this case. So this is going from steady level flight to a 75-degree banked steady coordinated turn. So over here, once again, x-axis is time. On the left, we have velocity, total velocity, Mach number, and our aerodynamic angles, alpha and beta. And then we have our orientation angles here in the middle, and then we have our control inputs. Now, the noise you see in this response, that's because this is implementing turbulence. Um, and so you can see some of the effects of that there. Now, something interesting is, if you'll recall back to these multiple trim solutions I was talking about, we had, the tail positive, tail negative, and tail near zero. This setup, and I apologize for not explaining this. This thin line, that's basically the trim reference values that we're trying to bring the aircraft through. And so you can see that's basically the reference signal we're trying to follow. And you can see over here, we're using the basically tail near zero trim solutions for our reference linearized control trim state, um, or trim control. And that begs the question, well, what if we used one of these alternate solutions throughout here? What if we use the tail negative? What if we use the tail positive? Um, something I'll bring up before I talk about that though is so just by way of note, it took place over 5 seconds, and it used 10 scheduling points, and we'll talk about that in a second. This is the response of the system. So once again, x on the y on the x, time on the x-axis, velocity, orientation, control. Over here, we're using the alternate trim control, so the tail negative solutions. Um, Now, with that response, we are able to bring the aircraft into the 75-degree bank. However, it takes much longer, whereas over here, with the tail near zero solutions, it took 5 seconds and 10 scheduling points that we linearly interpolate between. Over here with the tail negative, it takes 10 seconds with 16 scheduling points. And now I'll just mention that that's the flight path over here. Um, and so it takes quite a bit longer. It takes more scheduling points. So that's one drawback to using these alternate solutions. It does also beg the question, what happens if we use the tail positive trim solutions? Turns out it actually, even with 10 seconds, even with 16 points, even if we doubled 20 and 32 over here and use the tail positive solutions, we would not be able to bring the aircraft into a 75-degree bank, at least from what I've been able to see. And the opposite is true rolling the other direction. If we roll into a left turn, we can use the tail near zero solutions, but we can only use the tail positive alternate solutions as well. We can't use the tail negative. Okay, and I go into more detail on that in the dissertation. Okay, so now I'm just going to bring up the a couple tracking controllers. Now, the reason for looking at tracking controllers or the impetus behind them is stabilization. We're trying to stay about some trim solution, which is useful for just preliminary control analyses, but that's not what we're trying to do with an aircraft. We're trying to get it to follow some trajectory that's in the mind of a pilot or that's being planned by some path planner. The idea is rather than to stay about a trim solution, it's to minimize the error between um, our trajectory and the reference trajectory. In this case, we're doing it in terms of tracking body fixed rotation rates. The pilot is commanding PQ and R, and we're trying to follow what the pilot commands. So this is our system up here in terms of the aerodynamics. Now, the idea of this tracking control, in the dissertation, I look at a few different linear tracking controllers. This was the one that worked the best. And the idea here is typically for a traditional aircraft, we have some sort of a vertical tail with a rudder and some sort of horizontal tail with elevator. And so the rudder produces some side force like this, back and forth, and the stabilator produces some up and down force like this to be able to maneuver the aircraft. Now, you could kind of think of that like Cartesian coordinates. The BIRE aircraft, on the other hand, we have this tail that rotates about the fuselage axis. So for example, the stabilators are rotated right here. And and so it has some sort of a rotation component. And if those stabilators are deflected, they produce a force normal to that uh, rotated state. And so you can kind of think about that force being in polar coordinates, where the traditional version was a side and a up and down that would be summed together to give us this same rotated force. Now, what we can do with the BIRE aircraft is we can go back and forth between these two basically, and take this rotated force and go to these traditional side to side and up and down forces, if that makes sense. Now, that requires a transform, and this is the full control right here. So we have a little bit of PI input, and then we have a little bit of feed forward terms. And then over here, that's just our linearized trim. So we do that for this, Cartesian traditional system. And then we can do the inverse transform of that to bring it into the BIRE coordinates system, if that makes sense. So we'll take it from some pseudo aileron, pseudo pitch, and pseudo yaw control to, and aileron is the same across the two, to aileron, stabilator, and tail rotation. So just a couple interesting things about the gains. The aileron control is primarily dependent on roll rate error and integrator of roll rate error. The pseudo pitch command is primarily dependent on pitch rate error and integrator pitch rate error. and the pseudo yaw command is primarily dependent on yaw rate error and integrator of yaw rate error. Now, uh, the whole goal of this, there were several metrics that I use in the dissertation to evaluate these various controllers, looking at the eigenvalues, looking at time domain response metrics. But kind of the main one that seemed to be the struggling factor was being able to roll into and maintain a 60-degree bank in 2 seconds. Now, one difficulty of this transform with this controller is that when the trim stabilator input is basically zero, that transform has a singularity. And so you actually can't control with this controller of the BIRE on the BIRE aircraft with the CG at the nominal location. We actually have to shift the CG forward to have increased trim stabilator input. And you can see the value of it here. It's like, maybe 0.8, 0.9 degrees. Um, in order to even control the aircraft. So this response here, time is on the x-axis, on the y-axis. Over here on the left, we have error. So velocity and our rotation rates. I'll get to why velocity is there in a second. We have our orientation, so we roll to fit 10-degree bank in 2 seconds. And then over here are our control inputs to the system. Now again, black is command and control, gray is actuator state. So over here, the reason we have velocity is when a pilot rolls into a turn, they're not just changing the control surfaces, they're also changing their throttle setting. And so to more closely model that, I have just a simple SISO PI velocity feedback controller that's holding it at that trim velocity. And for more information, that's in the dissertation. Um, no, as I mentioned, we have to have some stabilator trim for this controller to work. And so one way to achieve that is to shift the CG a half foot forward. Um, but this begs the question, since the controller didn't work on the nominal system, are there things we can change to the system so that the controller could work? So one is shifting the center of gravity. So this is where it is on the BIRE aircraft. The center of gravity lies basically right in the middle between the neutral point and then the maneuver point. What if we shifted the center of gravity a half foot forward? What if we shifted a full foot forward? And so that's going to change the stabilator trim input. Another set of things we can look at are, I mentioned that the tail rotation limit was 50 degrees per second. What if we increase that to 100 degrees per second? What if we increase that to 200 degrees per second? Would we be able to control into these scenarios? For example, rolling into this 60-degree bank in 2 seconds. And then the last consideration that I look at in the dissertation is what if we increase the control effectiveness of the stabilators by 10 and 20%? Now, it's not 100% true, but you can kind of think about it like increasing the span of the stabilators by 10 and 20%. And so that's shown visually there. So I'm going to take a minute to explain this plot because we will look at more plots like this. So the shaded gray values up above are for the nominal, the controller on the nominal system. So that's, once again, that's these dark shaded gray bars. These transparent, smaller top bars with the black outline, that's if we shift the CG a half foot forward. And then down below it, this is with the hash, this is if we shift the CG a full foot forward. So coming back up here, this is the largest bank angle into which we can roll with a given controller in 2 seconds in sets of 10 degrees. And so you can see the nominal controller, we can't even roll into a 10-degree bank. And CG a half foot forward, we can go 40. Full foot forward, we can hit that 60-degree bank in 2 seconds. That's our desired metric again. Down below here, this is our non-zero initial condition regions of attraction for each of these system modifications. And so you can see as we move the CG further forward, our region of attraction increases in non-zero initial conditions of roll rate, yaw rate, and pitch rate. And then down here, this is our region of attraction with multiplicative aerodynamic model error. So this is an error, and I go into this in the dissertation. This is an error multiplied by, just basically a percentage multiplied by the aerodynamic values that come out of our forces and moments that the controller is not aware of. So it's basically looking at what if we're 10% off always in lift? How's that going to affect things? And so you can see our region of attraction, how that changes as we make these changes to the system and, and the controller. Now, once again, we have to shift the CG a full foot forward for this controller for it to be able to roll into and maintain a 60-degree bank in 2 seconds. Um, so maybe linear controls is not the answer. Uh, Past work again has seen that nonlinear model-based control may work better for rotating tail aircraft. So one controller I look at in the dissertation is nonlinear dynamic inversion. So this is again the aerodynamics of the system, not linearized, of course. And this is a state transform we can perform. And here's our full control here. Again, for the derivation, you can look at the dissertation. We have a PID controller with various feedback terms to give us a closed loop system. Uh, and so one of the difficulties of the previous controller, right, was that trim stabilator value being near zero. One of the difficulties with this controller is that we are taking the inverse of this non-constant matrix that's changing over time. And so if our determinant ever gets to zero, that will cause problems in the control. And I go into that in the dissertation as well. Okay, so interesting things about the gains. We have closed loop aileron control primarily dependent on roll rate error. Our stabilator closed loop control is primarily dependent on pitch rate error, and our closed loop tail rotation control is primarily dependent on yaw rate error. Okay, so representative response, we take the aircraft steady level flight, roll it into a 10-degree bank, steady coordinated turn. Again, time is on the x-axis, error over here, orientation, and our inputs over here on the right. Now, a couple interesting things that I'll point out. This has much higher peaks in the error response, particularly in roll, than the ITPI controller. That's the linear controller we just looked at, the control transform controller. And we'll take a look at these peaks in the tail rotation command when we get to the next controller. Now, with the CG at the nominal location without changing anything about the system, can we roll into a 60-degree bank in 2 seconds with this controller? No, we can't. We actually can only get up to 40 degrees bank. Now this, like I mentioned, we looked at a few different considerations as far as sensitivity are concerned. The first is, what if we shift the center of gravity a half foot forward, a full foot forward, and you can see the various properties up here. Excuse me. Now, the most interesting thing is that if we shift the CG at least a half foot forward, we can get into that, we can satisfy that metric of rolling into a 60-degree bank in 2 seconds. What if instead we increase tail rotation rate limit? So 50 degrees per second, 100 degrees per second, 200 degrees per second. And you can see that we don't quite get to the 60 degrees per second if we increase to 200 degrees per second, uh, 60 degrees in 2 seconds with the 200 degrees per second. You can see the effect on our regions of attraction, on our aerodynamic model error region of attraction. And then over here, the effects of our control effectiveness if we have the nominal system, if we increase it by 10%, by 20%. So the long story short, we have to, with this controller, we have to at least shift the center of gravity a half foot forward to be able to satisfy that 60 degrees in 2 seconds metric. So one last controller to look at. Maybe this one will be successful. So this is control allocation. So this is rather than determine what the control should be to give us some closed loop system, what we're going to do is we're going to rearrange this aerodynamic system to determine what the desired moments should be to give us this closed loop response, little v, and that's shown down here on the bottom. Now, this is a set given this desired moment, so we have a desired rolling, body fix moment, pitching moment, yawing moment. So that's a set of three equations, three unknowns, being our control inputs. We could use some sort of optimization or route finding framework to determine what our control inputs should be to give us this desired moment. Um, One nice thing, though, is with a couple simplifying assumptions, we can simplify this set of three equations, three unknowns, to one equation with one unknown. And so now we can use a root solver. And if we solve that equation for some tail rotation, we can we can get this closed loop control down here. Now I don't have the full control because the full control depends on solving this equation, on what the solution to that equation is. Okay, these closed loop gains are shown down below. So we have um, some, our closed loop aileron control is primarily dependent on roll rate error, yaw rate error, and integrators of roll rate and yaw rate error. Our closed loop stabulator command is dependent primarily on integrators of pitch rate error and yaw rate error. And our tail rotation command is dependent primarily on yaw rate error. Okay, so representative response, we're taking the aircraft from steady level flight, rolling into this and maintaining this 10-degree bank, steady coordinated turn. Time on the x-axis, error, orientation, control inputs. You can see we're able to get to that 10-degree bank. We actually have smaller spikes or peaks in the error uh, in this plot compared to the NDI controller. We also have a higher initial peak of our tail rotation command over here, but a lower final value compared to the NDI controller. And if we were to drag out time, that tail rotation command would slowly drop to 0. Okay, so with this controller, without changing anything about the system, can we roll into a 60-degree bank? No, we can't. We can only get to a 30-degree bank in 2 seconds without something blowing up or having issues or something like that. So again, this is looking at what happens, well, since we couldn't get to 60 with the nominal system, what happens if we shift the center of gravity a half foot forward, a full foot forward? What if we increase tail rotation rate limit from 50 to 100 to 200 degrees per second? And over here, what if we increased our stabulator control effectiveness from our nominal value by 10% by 20%? And the long story short, we could look at these other ones, but the main one I want to focus on is we can only get to the 60-degree bank in 2 seconds if we shift the center of gravity at least a half foot forward, or if we let the tail rotation rate limit be up to 200 degrees per second. Now, we talked about 3 tracking controllers, and of those tracking controllers, only 6 variants, with the sensitivity changes, um, only 6 variants are capable of achieving this roll to 60-degree bank in 2 seconds metric. The first was that linear controller if we shift the CG a full foot forward. The second 2 were the NDI controller if we shift the CG at least a half foot forward. And the last 3 are shown here if we shift the CG at least a half foot forward with the CAMA controller, or let the tail rotation rate limit be up to 200 degrees per second. Now, of those 6, only 3 of them uh, are able to roll into and maintain a 60-degree bank in 2 seconds when turbulence is implemented in the simulation. And that is each of these controllers with the center of gravity shifted a half foot forward. Now, you may be thinking, back when we talked about the why fighter aircraft fly unstable, um, and that has to do with right the maneuverability. And you may be thinking, well, doesn't shifting the center of gravity forward, first of all, doesn't it counteract maneuverability? And that's an excellent question. And the second question is, uh, is the reason that these controllers are successful, is it because we're moving the center of gravity far enough forward that the system is now stable in pitch? And the answer to that one is no. It's not that we're stable that's helping these controllers. Um, we could develop some sort of stability augmentation system for each of these controllers, and they still wouldn't work. Um, the difficulty here, again, lies in this trim stabulator input. As we have increased trim stabulator input, the difficulties with each of these controllers go away. So this one, it's that singularity in the transform. This one, it's the determinant of that inverse. For the gamma controller, it's actually a symptom of the root finding of this equation right here. We actually get multiple results when rotating and flying into these bank angles that generally have multiple trim solutions. And as we shift the CG forward, those multiple trim solutions actually uh, shift much further out in terms of bank angle. And so that's part of the reason that these ones are successful with shifting the center of gravity forward. Now, um, is there like a minimum magnitude for the trim stabulator input that we would be able to control? And I don't have a good answer to that. It could be, from what I've seen, it needs to be at least half a degree for the controllers to work. Um, but what if we limit our flight envelope to only those flight conditions where our trim stabulator input is greater than half a degree? Well, so the flight envelope for the BIRE aircraft is plotted here on the left. Actually, it's in both plots. So we have Mach number on the x-axis, altitude on the y-axis. Um, and so this left plot is showing the trim stabulator magnitude in terms of these contours. And uh, if we were to limit to say everything where the trim stabulator magnitude is greater than half a degree, that's basically everything darker than this shade. That includes this whole region, that includes this whole region right here. And so that really severely limits our flight envelope. So that's not really an option. So then, I wondered if we're trying that one of the benefits to removing the vertical tail from this fighter aircraft is decreased drag. What if we were to look at the drag difference between the baseline vehicle, so with that vertical tail, and with the BIRE vehicle with the CG a foot forward? So once again, CG's forward, we're going to have more trim stabulator input. That's going to increase our drag. Um, uh, would the drag increase be so much so that it's actually more than even the baseline vehicle? And the answer is generally no. So this is showing the drag difference over here on the right. Basically, what we want is these darker regions. We would want to fly in these darker regions. That's where our drag difference is negative. And so anything to the right of this zero line right here are the BIRE vehicle, even with the center of gravity a foot forward, is producing less drag than the baseline vehicle over here than the baseline vehicle. And so that's kind of a benefit. Even though we may need to shift the center of gravity forward, we are still producing less drag, particularly in this region. So this C2 flight condition, that's the one that I've looked at for most of the analyses in the dissertation. Um, and C3 up here. This is kind of these are kind of the combat region where this aircraft would dogfight. Okay, now just to wrap up a couple things. Um, so we have our linear stabilizing controller, and that we found one interesting thing I found was that it can stabilize without active use of the tail rotation control effector. Then I went into the gain scheduling linear stabilizing controller. Um, And so that looked at the tail near zero solutions actually worked best for rolling into a turn. And then we talked a little bit about a couple different tracking controllers, linear and nonlinear, and found no controllers were fully successful with the center of gravity at the nominal location, and only three of them, the ITPI linear controller and the two nonlinear controllers, were successful if we shifted the center of gravity a full foot forward. So there's a couple kind of paths that we're going down with this. One is to look at flight testing the RC vehicle, basically implementing these three controllers I've talked about on a subscale version and go out and fly it. Um, and then another avenue of future work is to look at different ways we may be able to change the BIRE system for improved control performance. One, like I talked about, is shifting the center of gravity a foot forward. There's an open question. Is that even viable? Is that within the envelope, the acceptable envelope of the CG location? The second potential solution is to increase our tail rotation rate limit to something pretty drastic, 300 or even 500 degrees per second. Another option is to add a little bit of dihedral on that rotating tail, so basically create a V-tail type aircraft. And I have a little case study in the dissertation where I look at that. Um, and these two are kind of tied together. This is the idea is what if we deflect the stabilators asymmetrically? Could that help with control? And then the last point is, what if we, instead of using an actuator to rotate the tail, what if we deflected the stabilators asymmetrically to use aerodynamic loading to rotate the tail and then lock it once it gets to the orientation that we need it at? And then the final thing that avenue for future work is to look at controlling the BIRE aircraft in various flight scenarios. So in this work, I've only really looked at steady level flight, rolling into a turn or stabilizing about a trim condition. What about takeoff? What about landing? What about mid-air refueling? Um, how would we control in those scenarios with this vehicle? And are there advantages or disadvantages to this vehicle in those scenarios? And then lastly would be taking the buyer aircraft, putting in a sim and sitting a pilot down and having them fly the buyer aircraft. And are there any maneuvers that the buyer aircraft can perform that a traditional aircraft, fighter aircraft could not perform? I'd like to thank the Air Force Office of Scientific Research and the Air Force Research Lab for funding this research. And I will take any questions in the comments. Thank you.